So this is a talk about applied proof theory. This is not an area where I can always assume that people have a background, so it's helpful. I always, at the start of my talks, try to give 5 or so slides, just giving an outline of the area, what we do, and then I'll go on to the actual subject of the talk. So with applied proof theory talks, people who've seen these talks before will recognize certain things. There are 2 rules, for 2 things you have to have in an applied proof theory talk. And the first one is this, the quote by Kreisel. You know, I've had some talks where I didn't include this quote, but I realized, no, I've got to stick with the tradition. And so the first slide always needs the Kreisel quote. And it's the motto of the area. What more do we know when we know that a theorem can be proved by limited means than if we merely know that it is true? All right? And so any mathematician will know that if you proved a theorem, the proof of the theorem will give you more insight than the truth of the theorem. It somehow explains why that theorem is true. But what Kreisel is getting at is, can we use proof-theoretic methods to actually produce something more? So can we give actual concrete mathematical new theorems that come from inspecting the proof? And can we use proof-theoretic techniques to get stuff out of those proofs that a mathematician wouldn't see? So people do applied proof theory without even realizing it, all right? So here's Euclid's nice proof that there are infinitely many primes. And so if you're asked in a pub, give me an upper bound on the nth prime number, what would you do? All right, so what is the nth prime number? You know it exists because of Euclid. And so if you're given the first n prime numbers, you can multiply them together, add 1, and that new number contains a new prime factor. Okay? And so you know that the next prime number must be contained in this Pn to Pn minus 1 plus 1. And so by iterating this, you can come up with a very crude upper bound on the next prime number. So this is a simple example of applied proof theory. So from the proof that there are infinitely many prime numbers, we've inferred a bound on the nth prime number. It's not always that simple. Okay? So the reason that we use these techniques from applied proof theory is that there are situations where you can have a really complicated theorem with a really complicated proof, and using proof-theoretic methods actually gets information from it that a mathematician didn't see. So this is another theorem about prime numbers due to Littlewood. There are these kind of analytic functions involving prime numbers, and this was a beautiful theorem of Littlewood that said that these functions change sign infinitely often, but when he proved it, the first point at which they changed sign wasn't known. And the reason, it's an utterly non-constructive proof. It uses a case distinction on the Riemann hypothesis. So you can't just look at this proof and work out when kind of numerical information from that, like you could with Euclid's proof that there are infinitely many primes. Okay? So Kreisel chose this as a case study for applying proof-theoretic methods, and he used some complicated proof-theoretic machinery to actually extract recursive bounds on the next sign changes. And this is in one of his papers from the 50s. And there's a nice quote from this paper, and I'm going to come back to that. Concerning the bound, it is to be expected from our principle, since if the conclusion holds when the Riemann hypothesis is true, it should also hold when the Riemann hypothesis is nearly true. And what's going on here is if you've got a non-constructive proof that's got a case distinction on something complicated, one way of getting around that case distinction is to kind of convert it into an approximate case distinction. All right? And I'm going to give you an example later on where we can show quite concretely how that might happen. All right? So it's very clever tricks. If sort of an ordinary mathematician looks at this proof, there'll be no idea how you get any kind of computational information from the proof. But if you have techniques that allow you to deal with non-constructive things like horrible case distinctions on the Riemann hypothesis, often you get something. Okay, so applied proof theory is now a fairly standard area. Most of you will have seen a talk in it. And so we produce papers routinely that allow us to get new, concrete mathematical proofs, mathematical theorems from non-constructive proofs. So this is just one of mine. I picked that just because I'm talking, and I can say without offending anyone that it's not hugely interesting. So the idea here, and you don't need to understand the details, okay? There's going to be lots of slides in this talk where you don't need to understand the details. I'm just going to point to the relevant things. So there was a really nice paper that dealt with a particular kind of mapping, and it showed that if in the interior of the fixed point set was non-empty, then fixed point exists, and the usual iteration scheme that you see in Banach fixed point theorem converges to that fixed point. The proof of this statement used all sorts of non-constructive reasoning, the existence of suprema and so on, and there was lots of nice geometric reasoning in it as well. And so applying proof theoretic methods in addition, so in conjunction with ordinary mathematical reasoning, one is able to get nice constructive information from this. And one corollary in the paper was a very, very concrete result that says, well, if you're in an LP space and we have some data on how big this fixed point set is, then there's a concrete rate of convergence in terms of sort of how close the iterates get to being a fixed point. And so for people in areas like functional analysis, optimization, it's actually really useful to have concrete computational information on how good your algorithm is. And a phenomenon here is that the rate of convergence, it's not something super complicated. It doesn't involve things like Ackermann functions or primitive recursive functionals or anything like that. It's just a simple polynomial, all right? So it's something that you would normally expect to get in a maths paper. When they show that you've got an algorithm that converges, you hope that the rate of convergence is just going to be some sort of polynomial, nothing horrific. And that's indeed almost always the case with results in this area, that what you get at the end is just some sort of simple polynomial band. Okay, so I'm just going to give a one-slide overview of the field, just detailing its history and the people who are working in it. So, as I said, the origins are in the work of Kreisel, actually the origins are in Hilbert's program. So the idea of finitizing mathematics, reducing it to a proper finitary system. And there were lots of tools that were developed then to try to do this. And so Gödel actually developed a technique that took proofs in piano arithmetic and reduced them to basically programs in system T. He didn't call it system T, but basically higher order programs. And these are relative consistency proofs. So people are much more inclined to believe that a higher order functional language is consistent than they are inclined to believe that piano arithmetic is consistent. And so reducing it to a simpler language, you're more inclined to believe the consistency. And what Kreisel observed is that while these techniques used to prove relative consistency were somehow used in a negative way, so if we don't have a proof of contradiction in this system, then we also don't have a proof of contradiction in this system, you can use them in a positive way. Namely, if we have an existence proof in the complicated system, we can turn that into a program in the computational system. And so the very same tools that had their origins in Hilbert's program can be turned on their head and used to extract programs from proofs. And that's typically how they're used today. So applications in mathematics, there are a couple of really crazy case studies in the 50s, very dramatic ones, Riemann hypothesis, theorems about prime numbers. But this area really found its ground when it was shown that you can consistently use proof theoretic techniques to produce new theorems in mathematics and publish those theorems in mathematics journals. So this was primarily due to Ulrich Kohlenbach and his collaborators. Around about the late 90s, they found the first really good seam of applications in approximation theory. Since then, it's been applied in all sorts of different areas by different people, so ergodic theory, convex optimization, and more recently, we're starting to see applications in algebra probability and back in number theory. So as there are more and more case studies, in parallel, one starts to see logical papers that describe what happened in the case studies in a general way. So if you found that for a certain kind of proof in a certain area of analysis, you kept being able to get good information, the answer is, well, why was this? Why did we get nice polynomial bounds? Why was it that all of these horrible non-constructive principles in the proofs didn't impact our ability to get quantitative information? And so typically these are then explained using logical meta-theorems that say, well, if you always have a proof of this form in this kind of logical system, if you have a proof in that logical system, then you get a reasonable program. And so these two things kind of go hand in hand. On the one hand, you've got pioneering case studies that try to bring proof theoretic techniques into new areas of mathematics. And then once you've got a critical mass of those, logicians start thinking, well, why was that possible? Can we explain that in general terms? So can we explain mathematical phenomena in terms of logic? So both of these are really interesting, and the interaction between those two things is really interesting as well. So this branch of applied proof theory is commonly referred to proof mining. I really hate that term because it gives the impression that you're just hammering away, right? You've got your proof, you've got a technique, you crank the sausage machine and something comes out. But it's really not as simple as that. So I wish they would stop using this terminology, but it's stuck. And actually, my grandfather was a coal miner, so it skipped a generation, but the family is back in the business. But just to be more inclusive, I mean, if one defines applied proof theory as just being the people who use proof theory and proof interpretations to get computational contents from proof or to understand proofs on a computational level, of course this is a much bigger area, and there are many people in the audience here who do that. So kind of constructive mathematics, formal program extraction, for example, being implemented in theorem provers, that's a really important area, and there's a nice alternative perspective to proof theoretic techniques in the book by Schrichtenberg and Rayner. Constructive dynamical algebra, I mean, these don't always use explicit proof theoretic techniques, but I think, often in this area, people look at the non-constructive proofs and try to kind of massage them to get some sort of computational equivalent out. And that's very much applied proof theory, even if you're not applying techniques explicitly, I would say. And of course, there's all sorts of areas that are connected to it, like higher order computability. And I should also mention that lots of techniques that are used in proof mining and applied proof theory in general, like the dialectica interpretation, negative translations, are studied in their own right and used for other things. So we saw negative translations yesterday, and dialectica interpretation, that's been applied from a categorical perspective. It's been extended to say things about programming languages and type theory. So there's a very rich world surrounding applied proof theory. I think I missed a slide. Yeah, so just some remarks before I go into the talk and present the explicit results I wanted to talk about. Proof theory is not defined by the use of any single technique. So it's not just about people who use dialectica or use realizability or anything like that. I think one should really define this area. It's thinking about and doing mathematics or computer science with a proof theoretic mentality. Finding new ways to apply proof theoretic thinking is really hard. And that's something that you don't necessarily see when you read a paper, right? So kind of if there's a paper that presents some new theorem in a particular area of optimization, one sees kind of what's been done, but what one doesn't see is the sheer number of papers that were read and understood to get to the point where one could find an area where these proof theoretic techniques do something. And so I probably read hundreds of, not in detail, but go through hundreds and hundreds of papers to try to understand an area, to try to get a sense of kind of where are the bits where looking at a proof as a proof theorist would help. And if they do, is it of relevance in that area, right? Is this an area where people care about bounds? All right? Do the theorems have the right form that what we could expect to extract would be relevant for the people in that area? So it's hard but really rewarding when it works out. And the research exists on a broad spectrum. So you've got some papers in this area that just look, that they're properly logical, right? So they introduce a type theory and they present mathematical results. Other papers just look like maths papers. And I've given talk where I've presented stuff that just looks like maths research. And people have asked, well, where is the proof theory? And that's a really good question. It's somehow there, but really done informally. And so one applies formal methods, but not in any kind of rigorous way. You do that in conjunction with ordinary mathematical reasoning. And I'm writing a paper at the moment where I'm trying to give a worked example of how this informal use of proof theoretic method goes. And I'm finding it really hard, because I know I'm doing proof theory, but I'm not quite sure how. And I'm trying to sort of design informal proof trees that explain what's going on, but it's really tricky. But this is a really rapidly growing field, so there's a huge potential both in expanding to new areas of application and also incorporating new techniques. And those are things I want to talk about at the end. So there's my short introduction. So the plan for the main part of the talk is to present the main topic, which are recursive inequalities. I'll explain what they are, and also why they're interesting for both analysts and applied proof theorists. And then I want to motivate a classification project I've been working on with my PhD students. So what I'm going to present is joint work with Kejineri. I'm going to present our main results and also explain where we want to go in the future. And that's probably the most important bit of the talk, which will be presenting things that we haven't done yet, but we hope to do. Okay, so recursive inequalities. And I'm going to motivate both recursive inequalities and the proof theoretic ideas that are associated with them via a really simple example. And it's the following. So forget everything that's gone in the talk so far. That was just a general overview of the field, and I'm going to try to make it self-contained from now on. So let's just pick some positive real number and a sequence of also positive real numbers that satisfies this recursive inequality here. All right? So it's kind of monotonicity with a constant. And so very natural question is, does this sequence converge? And if it does converge, how fast does it converge? And there are three answers to this question depending on the value of c. So if c is less than 1, then we essentially just have a contraction, right? At each element in the sequence, the next element is going to be less than c of the previous one. And so if we iterate that, that's eventually going to converge to 0. Okay, so it converges, and also you get a completely obvious rate of convergence. It's just c to the n. All right, so that's all very straightforward. If c is greater than 1, the sequence might not converge at all, because if we allow that, then we can get oscillating sequences. So that's fairly uninteresting. If c is equal to 1, we're in the situation that we have a monotonically decreasing sequence. We know it's bounded below, and so it must converge to something. But, yeah?
You said oscillating, but I would have thought it just diverges. It's greater than 1.
It could do as well. I mean, it could oscillate, it could diverge, it could do anything, but it may not converge. That's the point. But if c is equal to 1, we know it will converge, but there's a well-known fact from computable analysis that what it converges to may not be computable. In other words, it converges, but it may not have a computable rate. And this is a really interesting construction that involves somehow defining a sequence in terms of the halting problem. It's quite weird. And when you present people with this fact and they haven't heard it before, they somehow don't believe it. Yeah?
Computable in what sense? Using the sequence and C as oracles? Using the sequence as an oracle?
What exactly is the question? So,
in what sense do you mean may not be? What does computable mean?
A computable real number, so one where you can always find an epsilon approximation of that number in.
With mu n as data.
Yeah.
You can call mu n.
I mean, mu n doesn't. The limit is just not. It's not to do with mu n necessarily. I mean, it's.
So what's the inputs of this computability? So it's mu n and c.
No. Okay, it's not an algorithm. What I mean is that you can have a monotonically decreasing sequence, and the limit of that, just take the limit, that thing is not a computable real number.
Mu n was uncomputable.
The mu n can be computable. So that's the point. So the mu n can be a computable sequence, and the individual elements are rational numbers. So you know everything about the sequence. You can compute any point in the sequence to any level of detail, but the limit is not a computable number.
Okay, so you fix mu n and c in advance. They happen to all be.
Exactly. So it's an established construction. The Specker sequence. You can.
Is it all the same if mu n is actually? So you're not fixing mu n in advance, but mu n is somehow data. So it's like a function symbol t or something. You can call it to see certain values of it, and you just know this semantic property.
Sorry, I don't understand the comment.
But we can take this offline.
This is nothing like this is just a fact. I'll explain it after, like it's sort of tangential. It's weird. It's really weird. You kind of construct an infinite series where the individual elements of the series are defined in terms of whether the kth Turing machine halts on input k, and within a certain number of steps. And so you can always decide that. But if you had a computable rate of convergence, you could solve the halting problem. It's to do with that. So it's an explicit construction of the mu n, where the result would be if you had a rate of convergence, you could solve the halting problem. It could be that you do have a rate of convergence in this case, but there are examples where you don't have a computable rate of convergence. All right. So anyway, the point is that we can. I'll just write one thing on the board. Some chalk. So we somehow have this problem. The first question is, does it converge? So sort of yes or no. Oops. And if it's no, it's sort of uninteresting. And then if it does converge, is it with a computable rate? And then the answer to that could be yes, or it could be no. And even in a super simple, let's say I'm only going to, that's all I'm going to write on the board, so I can, just to keep it there. Even with a super simple case like that, answering this question is not entirely obvious, and it depends on the parameter of the recursive inequality. So why are these recursive inequalities useful? So this is just completely elementary analysis. Well, in this case, this is connected to the Banach fixed point theorem. So the Banach fixed point theorem says if we're in a metric space, we have a contractive mapping, then a fixed point of that mapping exists, and moreover, the usual iteration scheme converges to that fixed point. And so if we put aside for a second the existence of the fixed point, in terms of converging to that fixed point, we can essentially reduce that situation to the recursive inequality on the previous slide. Okay? Just because if we look at the n plus 1th element in this sequence, then kind of because that thing is a fixed point, then it's a contraction of the nth. And so we get exactly this recursive inequality. And the rate of convergence that we get from the recursive inequality is exactly the rate of convergence we get in Banach fixed point theorem. Okay, so the only point I'm making here is that this simple fact about monotone sequences of real numbers somehow underlies a theorem about metric spaces and non-expansive mappings and, and contractive mappings. So there's a concrete abstract mathematical setting that gets reduced to something much simpler to do with real numbers. So can we do anything in the case that we have non-computable convergence? So if we don't have convergence, we're not interested in it. If we do have convergence and it's computable, that's great, and we can use the rate in whatever setting we're in. So what happens if we have convergence, but we don't necessarily know that we have a computable rate of convergence? Can we get some sort of computational information out of that nevertheless? So the answer to that is yes, and it looks a bit weird. So this is a rephrasing of the case c equals 1. So c equals 1 is just that we've got a monotonically decreasing sequence of real numbers. We know they converge, but we're not quite sure to what. Okay? And that thing may not be even computable. So we can reformulate this. Instead of talking about the limit, we can just say that that's a Cauchy sequence. All right? So that's an equivalent formulation of this recursive inequality theorem for c equals 1. Here's a weird little proof of this fact that looks a little bit proof theoretic. And I'll explain where that's going in a second. So why is this the case? Well, if it's not true that a monotonically decreasing sequence of reals converges or is Cauchy, then there would exist some epsilon such that for any point, we can find two things after that point that are bigger than epsilon apart. Okay, so for any point, there's going to be two things that are bigger than epsilon apart. So that's just the contrapositive of the statement that that sequence is Cauchy, the reasoning by contradiction. And so now using a little bit of kind of logic proof theory, there's going to be some choice function, right? If for any n, we can find two things after it that are kind of bigger than epsilon, we can find, there's going to be some point at which we stop looking, all right? So we have some choice function. And so all we do is we just iterate that, all right? So we start with the first element. At some point, there's going to be two things bigger than epsilon. And then we go from here, we iterate again, and we get that. We iterate again, and we get that. And at some point, our sequence goes below 0, which is not possible because this is a sequence of non-negative real numbers. Contradiction, therefore, the sequence is Cauchy. You probably won't see this sort of proof in a maths textbook because, you know, why would you be taking this G out and doing things like that and making it unnecessarily computational? Because what we've got here, in this form of proof, we're actually, each step is very computational. We're saying kind of if we have a G that always finds the point where we've got two elements that are epsilon apart, we can iterate this, and we know after a certain number of iterations when we must get this contradiction. So it's a proof by contradiction, but somehow a computational proof by contradiction. So what's going on proof theoretically. Yeah, so just to state this is what we've achieved. So the original theorem just says if we've got a monotonically decreasing sequence of non-negative reals, that must be Cauchy. We've got a computational version of this, which is completely equivalent, which says that if we've got the same thing, then instead of Cauchiness, we have this sort of metastable convergence statement, where instead of saying that the sequence is always stable after a point, so always within epsilon after a point, for any g, we can find some sort of region where it's always stable in that region. So it's weird. It's a weird reformulation of Cauchy convergence. Logically, it's equivalent. And in this reformulation, we can come up with some sort of constructive analog, namely a bound on where we get this region of stability. Okay, so the extraction of rates of metastability, as opposed to rates of convergence, is a completely standard result in applied proof theory, which we do whenever convergence rates are not possible. And I'll explain why that's important in a second. They were also, really interestingly, independently discovered by Terence Tao. So this was used in some of his papers, but he wrote a really nice blog post where he talked about exactly this sort of thing and its significance in ordinary mathematics. So this isn't just something that's of proof theoretic interest. It was independently considered by mathematicians. So what's going on logically here? So kind of this thing looks a bit weird, but I can explain it in terms of what Shuangxi talked about yesterday, monads and negative translations and things like that. Okay, so we just do the double negation translation of the statement that a sequence is Cauchy. Okay, so the second row here is just the fully explicit epsilon delta definition of being a Cauchy sequence. We put two negations in front of it, and what we do is we just bring each negation into the interior one by one. So if we bring the first negation to the interior, the quantifiers flip. So that's the next stage. The for all becomes an exists, the exists becomes a for all, and so on. Okay? So now what we do is if we've got an exists for all exists, well, we know that there's going to be a bound on this exists mn, so we take that out as a function. So we're using a really weak form of the axiom of choice. And now we're saying that there exists an mn in this region here. So that's n up to n plus g of n, where this is not true. And then all we do is we bring the second negation back into the middle. The quantifiers flip again, and we get, for all epsilon and g, there exists an n such that there is this region of approximate stability. So going from ordinary Cauchy convergence to this weird proof-theoretic looking statement is nothing more than applying a double negation, doing some manipulations on the quantifiers. That's it. All right, that's the proof-theoretic explanation. But the significance is the following. The significance is that our original statement that the sequence is Cauchy has, in general, no direct computational interpretation, because a direct computational interpretation of the statement that a sequence is Cauchy convergence would be a rate of convergence. And the old result of Specker says that we can't necessarily get that. Okay, we don't necessarily always have that. On the other hand, a direct realizer of the double negation thing of this is exactly what we extracted here. It's a bound on the existential quantifier, and that's what's known as a computable rate of metastability. So the phenomenon here is that if in general you've got a statement that's proven by classical logic, you may not be able to get a direct realizer from it, but if you double negate it, do some funky business with the quantifiers, you can then often get a direct computational interpretation. And the idea here is that metastability is somehow equivalent to the negative translation plus dialectica of this statement. And I'm not going to go into the details of the dialectica interpretation, but for people who are interested in how that plays a role in this sort of area, it's essentially that. We put some negations in, and that's the double negative translation, and then we do some weird stuff with the quantifiers, and that's the dialectica. And if you do that throughout the proof, you often end up getting bounds for some reformulation of the theorem. All right, so back to Littlewood. So this is just the slide from earlier in the talk. This bit, it should also hold when the Riemann hypothesis is nearly true, right? What we saw just above is that we have taken Cauchy convergence and we've kind of reformulated it into an equivalent but approximate form of Cauchy convergence. So rather than permanent convergence, we've got sort of approximate intervals where you get stability. And this is exactly what the idea that underlies Kreisel's original case study. So rather than taking the proper Riemann hypothesis, he takes an approximate version of the Riemann hypothesis, and then the constructive information filters through the proofs. So Kreisel wasn't using the dialectical interpretation, he was using, I think, some form of epsilon calculus. But the idea is implicit in all sorts of proof theoretic manipulations of classical proofs. So replacing ideal objects with approximate versions of them. You know, also in constructive algebra, you see this without proof interpretations. If you've got the existence of a maximal ideal, you sort of convert that into an approximate maximal ideal. It's the same sort of idea you see in lots of different areas. So in my paper, I needed to go through metastability to get this concrete result. So this was a convergence property, a Cauchy convergence property. I needed to get the metastable version of that convergence property, and then from that, one gets a concrete, this is called a rate of asymptotic regularity. So this is a very concrete result that doesn't use any sort of weird proof theory, but to get that concrete result, one needed to go take the route via metastability. So metastability is important because if you use convergence as part of a proof of something else, the metastable version allows you to get direct quantitative information sometimes from the conclusion. All right? So even though this has nothing to do with proof theory, metastability, choice, or anything like that, one needed to go through metastability to get that. And this is a phenomenon that happens again and again in applied proof theory. And then this didn't come out very well, but this is just a screenshot of the blog by Terence Tao. And I really recommend this. It's super interesting because he's talking about a technique that was used, for example, in these proofs that there are infinite arithmetic progressions in primes, where one takes some bit of analysis and looks at a finitary version of this. And I remember when I was a master's student, before I knew any proof theory, I studied some of these proofs. There was a course on it. And they used a form of finite Fourier analysis, which was really interesting. And so this blog post is talking about this process of taking an infinitary statement in analysis and giving a finitary analog to it. And it explains where it's used, why it's important for mathematicians. And the example that he uses to illustrate this is exactly metastability. So this is just sort of a mathematical reformulation of what it means to be kind of a metastable sequence. And logically, it's equivalent to being Cauchy convergent. So this was independently identified as useful from a mathematical perspective. And actually, at the end of this blog post, if you look at the comments, a bunch of proof theorists have said, yeah, but we know this. And so there's a little bit of a dialogue there. It's really nice. Anyway, the main point in all of this is the following. So sequences of non-negative reals satisfying recursive inequalities, they may or may not converge depending on the parameters. Where they do converge, they may or may not do so with computable rates. The properties of these sequences can be used to get general convergence results for metric spaces or whatever, like Banach fixed point theorem. And when rates of convergence exist, you can apply those directly. And when no computable rates of convergence exist, one can often instead provide rates of metastability. And those are also useful. They're useful if you're an applied proof theorist, and they're also relevant sometimes if you're a mathematician. So those are the main points. So I'm now going to give some more examples of recursive inequalities, and I'm getting to the stage of the talk where I'm going to have slides with a lot of mathematical detail, but I promise you that it's not relevant. I really mean that. All I want to do is point to bits and just explain kind of how these recursive inequalities emerge in ordinary mathematical settings. Okay, so there are loads of examples to choose from. So recursive inequalities are everywhere in numerical analysis and optimization. I mean, there's literally thousands of papers that have these and use them, where you want to prove the convergence of some algorithm to some minimizer or some fixed point or some solution to a differential equation, whatever. And in order to establish convergence, you look at the complicated setting, you reduce everything to a simple property of real numbers, where the real numbers in question are always the distance between the algorithm, the individual points in the algorithm, and the point you want to approximate. And then you see what kind of recursive property they satisfy, and then you apply some sort of abstract convergence result. This is a really, really common trick in optimization and other areas to establish convergence. And so, in applied proof theory, the computational analysis of recursive inequalities in general has proved to be really important. So when I was doing this project with my PhD students, because our main topic was recursive inequalities, I felt I needed to understand the full extent of their use. So applied proof theory is one of those areas where it's still small enough that you can know about all the papers. You can, in theory, look through all the papers in the area. And so I looked through all of the papers, and there are about 25 of them that use some sort of computational study of an abstract recursive inequality. So I think the first was in 2004, and that's what it looks like. So it's kind of a bit more complicated than the monotone case, and there's some other conditions, and that's very typical. And then there were tons of examples last year. Here's another one. It's slightly different, and there's some properties here. Just wanted to give you a general idea of what recursive inequalities look like in the more interesting setting. So like I said, there's a bunch of papers in applied proof theory that studies these explicitly, and thousands of papers in ordinary mathematics that uses them. So I'm going to give some concrete examples, and these are from my own research, or they've been studied. So here's an example from, these people aren't logicians or proof theorists, they're just analysts. So the details are not important. All I want to do here is point out that if you know what a contractive mapping is, this is just a slight generalization of what it means to be a contractive mapping. Okay? So it's a slightly weaker property, and so things like the sine function satisfy this. All right, so they studied this particular kind of mapping, a psi-weakly contractive mapping, and it's just a generalization of what it means to be contractive. Banach fixed point theorem, it doesn't apply, but one can prove that these things converge to fixed points using a slightly more sophisticated proof. And there are various different algorithms as well. So rather than just using the so-called Picard iterate, which is where you take the first point and you repeatedly apply the mapping to it, you can also do weird things like that. You can take linear combinations of mappings, and these are really important in optimization, and often you can show that you get better rates of convergence for particular choices of the step sizes. But the long and short of it is that you have a general kind of mapping, you have an algorithm, you do a bunch of sort of elementary manipulations which just use properties of norms, so like the triangle inequality, stuff like that, and you end up with a recursive inequality, a slightly more complicated recursive inequality in comparison to what we saw before. All right, so that's all I'm trying to convey on these slides, is that in more interesting settings, you often do still get recursive inequalities, but those recursive inequalities are going to be a bit more complicated. They're going to reflect the setting that you're in, and they're going to involve components that are in your setting. So if you modify the algorithm so that you've got step sizes, then the step sizes are going to feature in your recursive inequality. So the question is, well, does this converge? And the answer is yes, but the rates of convergence are suddenly no longer obvious. All right, so with the Banach recursive inequality, if c is less than 0, you know that if you've got a contraction, you know that c to the n is going to be the rate of convergence, or a rate of convergence. It's not difficult to see that. A slight modification of the recursive inequality to something like this, and the rates you start to see in the mathematics literature are no longer elementary. You can no longer just stare at that and see that's obviously what the convergence rate would be, right? So here we're using things like the inverse function theorem, we've got some integrals, a bunch of properties that show that this thing converges to 0 as n goes to infinity. So it's no longer completely obvious. That's the only point I want to get across, all right? And what's more interesting is that at some point, analysts stop giving explicit rates of convergence because it becomes a bit too complicated. Like it's just no longer obvious how you get those rates of convergence from the recursive inequality. So, there's a slight generalization of this notion of being a psi weakly contractive mapping that just says it's asymptotically so. So rather than just being contractive, it says that kind of in the limit it's contractive. So you have some error term. All right, and so error terms are obviously really, really important in optimization. So if you add an error term, it roughly, in the limit, it becomes a weakly contractive mapping. You can still show that the usual algorithms converge to a fixed point and that fixed points exist, but the recursive inequality you get then involves an error term as well. And normally, when things like this are encountered in the literature, explicit rates of convergence are not given. So I've seen lots of papers where they have this recursive inequality. They say, okay, in special cases, we use this integral rate of convergence that we know exists from the other paper, but in general, we're just not going to give them. They can be given. And This was a paper that I wrote with Franciscus Wiesnert where we looked very carefully at the proof-theoretic structure of these convergence proofs and came up with a generalization that did give an explicit rate of convergence. And I've talked about this elsewhere. I'm not going to go into the details, but the point is that we were able to look at a very general class of mappings and give a slight generalization of that rate of convergence that existed in the literature that also applied to asymptotic variance and a bunch of other things as well. It looks similar, but it's a bit more complicated. And the key thing here is that we arrived at that by using sort of a careful proof-theoretic analysis of the underlying convergence proofs, many of which use classical logic. All right, so that's the only point I want to make there. There are other examples of recursive inequalities where no kind of rate has been given from the recursive inequality. So there's AI is everywhere now, so here's a simple gradient descent algorithm. One can show that simple gradient descent algorithms satisfy these recursive inequalities. The details aren't going to be interesting, but I just wanted to point out that if you have gradient descent, you can show that these recursive inequalities are satisfied. There are results in the literature that say that whenever we have a recursive inequality of this form with this little condition here, the beta n converges. In other words, f of xn converges to f of x star, where that's the minimum of the function. But the lemmas that state that all recursive inequalities of this kind converge, not only did they use classical reasoning, but they never provide rates, which looks suspicious. Okay? So those are just a bunch of examples of recursive inequalities in the literature. There are, like I said, sort of 25 to 30 papers in the proof mining literature that have used a quantitative analysis of recursive inequalities to get some sort of computational information from a general mathematical theorem. And using ideas from logic, you can do one of several things. So sometimes, by looking at the proof, you actually get rates of convergence. They weren't stated in the mathematical papers, but if you kind of carefully look at the proof-theoretic structure of that proof, you can often generalize them and give more generalized rates of convergence. You can also prove that in some cases computable rates don't exist. And that's interesting, because then you explain why, in certain cases, the mathematicians who've been proving these results just say, well, yeah, we don't have rates of convergence in this case. You can actually say why that wasn't possible, why by looking at the proof it wasn't possible to get computable rates. And then in this case, one can produce computable rates of metastability instead, very often. So I finish at 1:15, right? Yes. Cool. Yeah. Okay, so I'm going to go very quickly through. So I presented the main idea of recursive inequalities and why they're important, and that was sort of one of the main aims of my talk. So I just want to flash some things that we did in the paper just to show you, and then I'm happy to talk about these with anyone afterwards. So the idea of a project was a systematic study of recursive inequalities. So rather than taking a problem, reducing it to the recursive inequality and studying that, why not look at a general class of recursive inequalities and ask general questions about when do they or don't they converge, when do we or don't we have rates of convergence, and can we produce them, and if not, can we produce rates of metastability? So this was the project. So we look at a general class of recursive inequalities and ask, when do we get convergence results? And if so, can we strengthen those results? If we suspect that general rates of convergence don't exist, can we prove this? Can we analyze these proofs and produce either computable rates of convergence or metastability? And then can we use this to prove new theorems in sort of proper mathematics that talk about things like maybe gradient descent algorithms? So this is a nice project because it brings you through sort of elementary analysis, computability theory, proof theory and constructive maths, and also applied proof theory. And that's why I worked on it with my PhD student, because it also gave him a tour of all of these different areas. It was a really nice project to work on with somebody just coming into applied proof theory. So what we looked at in this paper were sequences of non-negative real numbers satisfying this very abstract recursive inequality. And all of the examples I gave are instances of this recursive inequality. So the alpha typically always step sizes, and the gamma are typically error terms. Now, this alone is too weak, so you don't get convergence of anything here with just those conditions. But if you add further conditions, then you do get different classes of convergence results depending on which conditions you add. So what we were doing in this paper, we're just looking at the different classes you get depending on different additional conditions. And so the main two categories we looked at were when, rather than the gamma converging to 0, the infinite series generated by the gamma converges, which is stronger. And the second one was that the gamma divided by alpha converges to 0. So each of those two things, and that allows you to say stuff about the convergence of mu or the convergence of beta. And so we just studied that quite systematically and tried to establish exactly what you needed to prove convergence and when you didn't get rates of convergence. So I'm just going to flash a bunch of results to show you what sort of thing we're doing. One subclass of this recursive inequality is really important in proving convergence of gradient descent type algorithms. For the simple gradient descent, one can show that it reduces to a special kind of, this kind of recursive inequality. But there's really sophisticated gradient descent methods that also reduce to this recursive inequality, and that's primarily where it's used. It's to establish the convergence of kind of quite complicated gradient descent methods. So I'm just putting that there just to show that you can generalize these quite interestingly. Instead of looking at the derivative, you can, if you've got a convex function, you can look at the subderivative, or you can look at an approximate version of the subderivative, and then recursive inequalities are really important for establishing convergence. And there was a really nice paper on the convergence of one of these gradient descent type algorithms where the authors say they establish convergence, they also have some sort of subsequence convergence result, and then they say this result does not give any information on the asymptotic behavior of f of xn outside of blah. Right? And so they just state this. And so the suspicion is that the recursive inequality they're using, although you get a convergence result, you don't get a computable rate. But actually proving that is really hard. So we adapted this Becker construction to the particular case of this recursive inequality, showing that in general you can have a bunch of things that satisfy those conditions, but none of the convergence results come with a computable rate. And that's sort of a 3-page proof. It's not easy. It's not obvious trying to embed the Becker sequence construction into concrete cases, but once you've done that, you've given an explanation as to why it was not possible to extract, just by looking at the proof, get rates of convergence. So it's kind of, this is not so much to do with applied proof theory of the extraction of bounds. It's an explanation of why, whenever you have this, you can't automatically get rates of convergence by looking. We did a bunch of strengthening results where we showed that kind of when you have a convergence result of the form, if whenever we have this condition we have convergence, we came up with an if and only if statement where we showed, okay, in this situation, this is the exact characterization of what you need to get convergence. So I'm not going to talk about that too much, but this is one of the bits of our project where we're just doing analysis. We're not doing any proof theory or computability theory. We're just strengthening these and trying to get the most general quantitative results we can. We're giving quantitative analogs of these. So the only thing that's important here is we're basically getting rates of metastability for this recursive inequality. So just like there are rates of metastability for the simple monotone decreasing sequences, we can get those for these more complicated recursive inequalities, but just the rates of metastability are correspondingly a bit more complicated. And now we come to the second thing that always needs to be in an applied proof theory talk, and that's a theorem that's so complicated it spreads over multiple slides. So here it is. So the details aren't important, but the point is that once we've done this sort of computational analysis of recursive inequalities, we can then use that to prove numerical facts about complicated algorithms. So we gave a very, very general gradient descent type algorithm. So we defined exactly what abstract properties an algorithm needs to kind of look like a gradient descent method and reduce to this recursive inequality. We give a convergence result, and then we also give a rate of metastability for that. And then that rate of metastability can also be used to prove sort of regularity results as well. So it's not just an abstract proof theoretic thing. And so this projective subgradient method I flashed up on the slide, that falls out as a special case of this. So that was the project. I'm not going to make you suffer through the horrible details of this paper. Like all projects in this area, kind of there's a lot of mathematical detail, a lot of proof theoretic detail, but I just wanted to convey kind of what we're doing, what the results look like, and why they're interesting, and what methods we use to get them. But in the last few minutes, what I want to do is explain where we're going in the future. So while we were writing this paper, we discovered a paper that was being written in parallel, just in the maths community, nothing to do with logic. And it was really like, well, my first thought was like, oh my God, have we been scooped? But of course we hadn't, because they weren't doing applied proof theory, it was just mathematics. And this is one of these really nice realizations that what you're doing is somehow being done in parallel by other people, and that probably reinforces what you're doing. So this was a survey article just about convergent sequences, so just about recursive inequalities in the literature, trying to survey where they came from, where they were used, and the differences between them. So this doesn't focus on rates of convergence or metastability or anything like that. It's just mathematicians looking at this from a kind of giving a broad overview of the field. It's a really nice paper. So they give kind of big, complicated tables of kind of various different recursive inequalities in the literature and then what they're applied for. And so the one that we looked at for gradient descent is just this one here, proposition 3.16, but it's just one of many. They also give sort of tables that classify these recursive inequalities based on different mathematical properties, so the leading coefficient, the noise term, things like that. And really interestingly, they also give general heuristics for how those are used. So kind of, you know, if you've read enough of these papers, you realize kind of there's just a technique, and they outline really nicely what those techniques are for using these recursive inequalities. So it was a really cool paper. I was really happy that this got released once we started writing the paper, and of course we cite it now and talk about it. But this brings me nicely to thoughts for the future. So there's a bunch of recursive inequalities. We've studied a few of them in applied proof theory, but there are a lot of interesting ways to go here. So one really interesting possibility would be to look at stochastic recursive inequalities. So those haven't been studied at all in applied proof theory. We just look at sequences of real numbers. So stochastic recursive inequalities look very similar, but what we get is we get that all of the properties are true almost surely, and then the convergence result is also an almost sure convergence result. These are really interesting and difficult from a proof theoretic perspective. So ordinary convergence, non-stochastic convergence is, well, it's for all exists for all. And so you can kind of manipulate those quantifiers and get something reasonable out. Almost sure convergence is, logically speaking, much more complicated. And so even trying to formulate the correct way of looking at this from a finitary perspective is non-obvious. And then the proofs of these convergence results tend not to use elementary analysis. They almost all rely on things like the martingale convergence theorem. So automatically the proofs are much more complicated. So there is some precedent in the literature. So Jeremy Avigad and some others have looked at martingale convergence theorems and tried to give quantitative versions of those proofs. And so what my PhD student is looking at the moment is trying to take the ideas that are there in the proof theory literature and incorporate them into giving finitary analog of some simple stochastic recursive inequalities. And this stochastic recursive inequality is called the Robin-Siegmund theorem. That's so important in probability theory that it just tends to be shoved in the appendix of textbooks. It's just absolutely essential. And so once we give a quantitative version of that, we maybe have some way into giving interesting quantitative analogs of a lot of results in stochastic optimization. So that's the first interesting direction of future research. A second is, of course, formalizing all this stuff. All right, so there's a lot of stuff on formalized program extraction so far. Of course, there's Minlog, and people like Professor Schrichtenberg and Ulrich Berger have been doing this for a long time. But I'm only aware of 3 people developing libraries specifically for proof mining, so applications in analysis. So there's someone in Bucharest, Horatio Cavall, who's got a really nice lean library now that does a lot of things. It's formalized dialectica, but also it's formalized actual proper proof mining results. So it's formalized almost an entire paper in applied proof theory, which is no mean feat. Angeliki Kutsuko-Agiraki has got, she's written a lot about this, so she's working with Isabel, and she's written a lot about the virtues of having a library of lemmas that have constructive analogues that you can use to potentially automate parts of program extraction. So I really recommend reading this paper. That was in CIE. And my own PhD student, I mean, he's from this generation where they just learn formalization as undergraduates. He went to one of the Kevin Buzzard summer schools, and so he already knew how to use Lean when he started. And I said, well, why don't you formalize some of these? And he's like, okay. And then one afternoon, he's done it. So it's incredible. I'm too old to do this, but Keji's. So
You are never too old.
okay, I'll tell myself that. So, you know, the specific idea I'm getting at here is that you've got a bunch of recursive inequalities. These are really important in both optimization and in applied proof theory. So we can start building a catalog of formalized versions of these recursive inequalities in an effort to formalize bigger parts of both nonlinear analysis and applied proof theory. And the point is that, you know, you don't even need to rely on advanced libraries for this. You just need to know basic facts about for most of these recursive inequalities, the non-stochastic ones, it's just elementary analysis. So you don't need to have learned a load of Lean to be able to do that. And so this could even be a project for good undergraduate students where they do something that has some sort of meaning, but which could realistically be done in a few months. So it'd be really nice, to, and we're starting to build these libraries, but hopefully within a few years we'll have a good basis to formalize more analysis in applied proof theory. And the final idea, which is, so that's just an example, it really exists. The final idea, which there's no initial work here at all, so this is really wishful thinking, but I'm really interested in it nevertheless, is to apply automated reasoning. So when these convergence theorems are reduced to recursive inequalities, typically all that's involved in reducing them to the recursive inequality are basic facts about norms or the sequence or anything like that. So it seems very elementary and very sort of simple in the sense that you're not using much mathematically. It's often very complicated computationally. But it strikes me that this could be a good opportunity for designing automated reasoning algorithms that kind of just try to search for a reduction to a recursive inequality at least, and then use an existing catalog of convergence results to try to finish the proof. And then, of course, if you do have rates of convergence or metastability for each of these recursive inequalities, then you'd also get those as a side product. So it'd be really interesting to see if automated reasoning can do anything here and potentially generate convergence results in this area, just because so many convergence results have such a similar form. And the key bit of the convergence proof is always the recursive inequality rather than the reduction. And, you know, together these three things reinforce each other, right? On the one hand, you're looking at trying to understand the computational properties of more complex recursive inequalities, you're formalizing them in a proof assistant, and on top of that, you're trying to develop some kind of new algorithms for maybe automatically doing the reduction and using the library that you have to finish the proof. And so these three things together, I think, make a really fascinating project. And that's where I want to end.